In this problem-solving screencast, we are asked to consider the molecular formula C4H9Cl. The prompts are: how many isomers can you propose, to name them, and then determine how many unique carbons and hydrogens there are for each. So before we get into it, why don't you pause this video and consider this prompt, see how many you can come up with, then leave a comment below the video, and then we'll go through the video and then you can respond to your comment and see if you were right or not as a discussion to other people watching this video. So let's go ahead and get started. First, we're going to rewrite our given molecular formula. C4H9Cl. And what we want to do is determine the degrees of unsaturation present in that molecular formula, because that's going to help us be inclusive or exclusive about what potential functional groups we can propose. So when there's a heteroatom, specifically a halogen, in the molecular formula, that is going to add to the hydrogen count. So let's write that down. So our revised molecular formula is going to be C4H10. So what we've done, we've counted the chlorine as a hydrogen. So remember that we want to use the alkane formula, CnH2n plus 2. For our compound, n is equal to 4. So we have C4H 2 times 4 plus 2. That gets us C4H10. We calculated, we have C4H10, so we subtract that. And essentially we're going to get 0 degrees of unsaturation. So H10 minus H10 gives us 0. So no matter what we propose, there can be no pi bonds or no rings. So the way that I like to consider this type of problem is, because there are no degrees of unsaturation, we're going to start with a C4 chain. So what I want to do here is just categorize the longest carbon chain. It's going to have 4 carbons, so we can draw that out. So there's 4 carbons. This hydrogen count is now C4H10, but we know we have to substitute a chlorine in there. So we're going to remove one of the hydrogens, replace it with chlorine. Let me go ahead and number this so that we can follow this logic. And we're going to put the chlorine at position 1. We want to be very logical so that we get all the possible isomers. So the name of this compound is going to be 1-chlorobutane. So then we can also put the chlorine at the 2 position. So we're going to draw that. 1, 2, 3, 4. Chlorine goes at the 2 position. So now we have 2-chlorobutane. Let's go ahead and now consider, we've exhausted all the possibilities for a C4 chain. If you put the chlorine at position 3, you're really making 2-chlorobutane again. It depends on which way you number the chain. So we're going to go down and we're going to write C3, and we're going to have a 3-carbon chain. 1, 2, 3. And so now we have a chlorine and a methyl group to consider. The methyl group can really only go at position 2, because if we put it at 1 or 3, we're just making a 4-carbon linear chain. So we have to put the methyl group in. Let's put the chlorine at position 1. And so now what we've done, we have a 3-carbon chain, so it's a propane derivative. The substituents are chlorine and methyl, and so we name these alphabetically in the chain. So we're going to have 1-chloro, 2-methyl, propane. So what about putting the chlorine at position 2? Again, we have to leave the methyl group at position 2. So now we're going to put the chlorine at position 2. And we're going to come up with essentially the same name, but the locant number is different for chlorine. So we have 2-chloro, 2-methyl propane. So our first approximation, we would say there's 4 constitutional isomers for C4H9Cl. However, if we examine a little bit deeply, one of these structures, we can see that there's actually stereoisomers. And so the one that is going to be is the 2-chlorobutane is actually going to have stereoisomers at this 2 position. And the reason that is because we have a carbon, which is a stereogenic carbon, bearing 4 different substituents. So let me write those substituents in green. That carbon, which I've highlighted with the blue asterisks, has a methyl group, it has a hydrogen, it has a chlorine, and it has an ethyl group. So these 4 different unique groups make that a chirality carbon. So we sort of use these words interchangeably. It's a carbon bearing 4 different groups. So we can now draw that 2 different ways. So this is the stereoisomers of that compound. We can have the chlorine coming out towards us, and then the hydrogen, which we have not shown, is going towards the back. So what we're going to do right now is draw the mirror image of that. And to do that, we're going to draw this ethyl group. We're going to draw the chlorine coming out, and then this hydrogen going back. So those are now mirror images of one another. And what we want to do now is, because they're both 2-chlorobutane, we want to figure out how to name each one of them. And the way that we're going to do that is look at the atoms directly bonded to the chirality center and give them a priority according to the periodic table. So chlorine's going to have the highest atomic number, so that's going to get the highest priority, which I'll call 1. I'll just go ahead and label that for both cases. The hydrogen with atomic number 1 gets the lowest priority of 4. And if we look at the 2 other atoms bonded to that chirality center, they are both carbon. So what we have to do is look at what's bonded to each of those carbons. We see that the methyl group has 3 hydrogens. This other carbon, which is a part of an ethyl group, has another methyl group. So this is going to be 2. Then the methyl group itself is going to be 3. And to do this correctly, the lowest priority group has to point away from you, which it is, as we've shown by the dashed bond. And so then what you determine is the order in which these are moving. So the one on the left here is going in a clockwise pattern. So this is going to get the R stereochemistry. So what we can say is this compound is parentheses R 2-chlorobutane. The other compound, we are going counterclockwise, so this is going to be S. It's the mirror image enantiomer. So this is going to be S 2-chlorobutane. So these 2 stereoisomers are mirror images of one another. They have identical physical properties. The only difference between them is the direction in which they rotate plane polarized light. So we've answered the first question, the first prompt, completely. We've figured out there are 1, 2, 3, 4, 5 different isomers that we can draw. We have an enantiomeric pair, which consists of 2 stereoisomers. We've then named them using the Cahn-Ingold-Prelog convention. And the last thing we want to do is determine how many unique carbons and hydrogens there are for each. So let's go ahead and do that as an exercise to keep sharp on concepts of NMR. So what I want to do is draw basically a set notation where I'm going to put the number of unique carbons, then the number of unique hydrogens. So for 1-chlorobutane, we have 4 unique carbons and then 4 unique sets of hydrogens. So let's just draw that like this, 4 and 4. For each of the 2-chlorobutane stereoisomers, we are also going to have 4 unique carbons, 4 unique hydrogens. For 1-chloro-2-methylpropane, we are now going to have 3 unique type of carbon and 3 unique type of hydrogen. For 2-chloro-2-methylpropane, we have 2 unique carbons and only 1 type of proton. So let's redraw these at the bottom here and dig a little bit deeper into the unique number of hydrogens for each and determine a ratio. So of the 1-chlorobutane and 2-chlorobutane, since they both come out to 4 and 4, at this point you really couldn't differentiate them until we did a little bit deeper analysis of the proton sets. The other two are 3 and 3 and 2 and 1. So we could look at spectra and differentiate those from the 1 and 2 chlorobutanes. So here's our 1-chlorobutane. And all we're going to do to determine the ratio of these hydrogens of the 4 unique is just count. The 1 position has 2 hydrogens, the 2 position has 2, the 3 position has 2, the 4 position has 3. So of this number here, we're going to get a ratio of 2 to 2 to 2 to 3. Then for both the R and the S 2-chlorobutanes, they will have the identical NMR spectra. Again, the only way you can differentiate them is through optical rotation using plane polarized light. Let's go ahead and look at the 2-chloro. And we said this was also 4 and 4. Let's go ahead and determine the number of hydrogens on each carbon. We have 3. 1, 2, 3. So the ratio or integrations would be 3 to 1 to 2 to 3. So now we could differentiate the 1-chlorobutane from the 2-chlorobutanes based on the proton NMR spectra, and the peaks would integrate differently. So we already know that the C3 chains give 2 different types of sets, 3 and 3 versus 2 and 1, but let's go ahead and determine the ratios anyway. So this 1-chloro-2-methylpropane, we said was 3 and 3. If we determine the number of hydrogens, we have 2 to 1. And then these 2 methyl groups, with each having 3 hydrogens, are going to be equivalent. So we could write a ratio of 2 to 1 to 6. Because the 2 methyl groups are equivalent, we're going to count them as such. And then lastly, the 2-chloro-2-methylpropane. We said there were 2 unique type of carbon and only 1 type of hydrogen. So if we count these methyl groups, 3, 3, and 3 are all equivalent. So this is going to be a singlet that integrates to 9 hydrogens. So in this exercise, we've looked at C4H9Cl. We've proposed isomers, we've named them, we've used the Cahn-Ingold-Prelog rules, and then we've revisited carbon and hydrogen uniqueness in relationship to differentiation by protein. If you like this screencast, please hit the like button and leave a comment. If you like this channel, please hit the subscribe button and you'll be updated when new videos and screencasts are uploaded.